This is Geometry Unit 6, Lesson 2 on proving triangles congruent using side angle side. Now in this unit we are going to be looking at the different ways to prove triangles congruent. But we need to know, what does congruent actually mean? We talked about this a little bit in the last unit. Two polygons are congruent if they're the same size and shape. But what determines the size and shape? Well, the shape is determined by the angles, so all corresponding angles would have to be congruent. One angle matches the other, all in all different order. And all of the corresponding sides are congruent. That makes them all the same size. So, in order to prove polygons congruent, all the angles and sides have to be congruent, the ones that are corresponding. So, just to remind us, if triangle ABC is congruent to triangle PQR, then all pairs of corresponding parts are congruent. So let's look at the angles. Now remember, triangle congruence is based on what you are given here. So if we have angle A, according to this congruent statement, it should be congruent to what angle in the other triangle? Well, according to this, A should be congruent to P. So angle A is congruent to angle P. Angle B will be congruent to angle Q. And angle R, angle Q, and then angle C will be congruent to angle R, because they're in the same place, corresponding. So correspondence is given there. Now that's the angles that are congruent. Those three angles are congruent. And then the three corresponding sides are also congruent. We can also get that from the congruent statement. If we say side AB, that should be congruent to side PQ. So here's AB, here's PQ. If we do side BC, BC is here, will be congruent to PQ, which is, or excuse me, QR, which is over here. And then the third side is AC, will be congruent to PR. Here's AC, make three hatch marks there, and then PR there. So that proves that all three triangles are congruent. Now, we can also prove this using rigid motion. If there is a rigid motion for which the image of ABC is PQR, then the triangles are congruent. Now, what that means, remember with transformations and a rigid motion, that means that all of the sizes and shapes are preserved, okay? Because distance and angle measure are preserved when we have rigid motions. Okay, so using reflections, rotations, and translations, we want to get ABC to line up perfectly with PQR. So, let's review how we do that. If we take ABC and we translate it along the vector AP, so we start at A and we go to P. Let me do it in a different color so you can see what I'm doing. And if you go from A to P, translate along like that. Do a red one. There. Try it again. There we go. I'm going from there to there. All right, and you can see when I translate it along that vector AP from A to P, P ends up here, or excuse me, A ends up at P. B becomes B prime and C becomes C prime. All of these are going to move exactly the same way. So we're sliding this up to here where the dotted one is. Then we are going to rotate counterclockwise. CCW is counterclockwise. Counterclockwise means we're going to turn this way around P. So P is going to be like our center hub, and we're going to turn this around like this so that this triangle here, our rotation, PB prime coincides with PQ. So PB prime here, we rotate around like this, so it comes out to be PQ like this. So that means that PC and PC prime will line up, and PC double prime and Q will line up. So we now have this. And then we want to reflect over PQ. So this triangle will actually become the third triangle, which is right there. And there's your reflection over PQ. And that triangle ABC becomes PQR. So, you can prove it by proving all the sides and angles or using rigid motions. Okay, but there is a slight problem with proving rigid motion to do congruence. Saying two figures congruent if one is the image of the other under rigid motion is a good definition of congruence, but it's not always a convenient method to prove two figures are congruent. So, are these triangles congruent? Well, they kind of look like they are. Here's ABC and DEF, this triangle right here. They kind of look like they're congruent. So if we take this triangle and map ABC onto DEF, all right, so if we translate along AD, so I'm going to go along AD like so. All right, so I translate along AD and till I get here, so this becomes B prime, C prime, D prime. All right, and then rotate clockwise, so this time I'm going to go this way, around D until AB prime corresponds with E. So this is going to go around like this until it hits like so. So this is going to rotate down, hopefully, until it ends up there. But how do we know that they're lining up perfectly? Well, it's kind of hard to tell. You can see it kind of overlaps here, but we can't really tell if it works. So it's not always the most helpful way of doing it. So by itself, the transformation doesn't prove congruence. We have to do something else. So what we're going to look at is why certain way will work and the other ones will not. So we're going to look at the first one. All right, now the congruence will work if certain pairs of corresponding sides and angles are congruent, and we don't have to prove all of them, we just have to prove certain ones of them. But before we learn which ones, we need to know some terms. I'm going to be referring to included angles and included sides. All right, an included angle is the angle formed by two consecutive sides of a polygon. So here's my polygon, my pentagon actually, pentagon horse. All right, so the included angle between sides RS and SE. Here's RS and SE. What would be the angle that's between those two sides? Well, that would be angle S right there. It is formed by where the two sides meet, the endpoint. So this is going to be at angle S. Included means between. So between the sides. Okay? And an included side, it's the side between two consecutive angles of a polygon. So if I look at two angles of a polygon, so say I look at angle H and angle O, right here, okay, what side is between those two angles? All right, well, the side that's between those two angles would be this side right here. So that would be angle OH. So included means basically between. All right, so now that we know the vocabulary, let's get to proving that two triangles are congruent by the first method. We have many ways of proving triangles congruent. The first one is called side angle side, or SAS postulate. The side angle side postulate says if two sides and the included angle of one triangle are all congruent to the corresponding sides and angles of a second triangle, then the two triangles are congruent. So SAS, you have to have two sides and the angle between them congruent. So in order for that to work, two sides and angle congruent between them, we're going to prove why it works, and then we'll actually be applying that. So if I'm looking at these two triangles, if we have AB here congruent to A prime, B prime, AC is congruent to A prime, C prime, and angle A is congruent to angle A prime. Sorry, A is here, A prime is there. All right, so that is side angle side is corresponding to side angle side, so that's congruent. Now, we just said we don't know if they actually do correspond, but we're actually going to prove that they do. We're going to use rigid motions to prove that this triangle is really congruent to this triangle. So we want to make sure that all the points are going to coincide. So let's take a look at how this works. So what we want to do is we want to get this triangle and this triangle so that A corresponds to A prime, B corresponds to B prime, and C corresponds to C prime. If that is true, then we can use side angle side to prove that triangles are congruent. So let's see what happens when we do this. So we want to prove these two triangles are congruent and it'll match up perfectly. So the first thing we're going to do is we're going to take A prime here and we're going to translate it over to A. So if you translate, we're going to slide from here down to here. So that means A prime ends up at A. So we know A prime and A are going to correspond to each other, so we're good there. Okay, now just to work the other pieces as well, where does B prime end up? Well, it actually ends up at B double prime down here. And then C prime ends up at C double prime down there. So we're now at this triangle right here. So we're going to take this triangle right here. We have made A correspond to A, so we're good there. That's what we want. So now we have to get B prime to correspond to B. Well, if we rotate clockwise around A until AB prime corresponds with ray AB. Well, we're going to get this to turn like this so that AB prime, double prime, ends up at B. So it's going to look like this. Okay, now how do we know that B will coincide perfectly with B prime? Well, the reason we know that because we were given that AB and AB prime were the same length. That was the original given. So if these pieces are the same length, if this piece and this piece are the same length, it's going to correspond to here. They're going to be the same length. So that corresponds up like this onto here. So they're going to be the same length. And that means B double prime now becomes B. So we've gotten A to correspond, we got B to correspond. Now what we have to do is get C double prime, triple prime to correspond to C. Well, if we flip-flop this over here, reflect it over AB, won't C prime correspond with C? Yeah, it will. And because, remember, the angle BAC and B prime, A prime, C prime here, the angles didn't change. When you do a rigid motion, they don't change. So this and here and here. Because the angles are congruent, the ray will correspond with area AC, and since AC is congruent to AC prime, C triple prime ends up at C. Therefore, the image of A prime, B prime, C prime is triangle ABC. So A is A, B is B, C is C, so therefore the two triangles are congruent. So what we've just proved is the side angle side postulate. We can now use this postulate to prove triangles congruent. Now, you're not going to have to use rigid motion to do this. We're actually going to be doing proofs. So this is what we have to do. Now that we know that side angle side proves triangles congruent, because we just proved it using rigid motion, what we have to do is get a pair of sides and congruent and prove that the angle between them is also congruent. So if I want to prove triangle ABC is congruent to angle DEF, suppose I had side AB. What side would that have to be congruent to in the other triangle? Well, it would have to be congruent to triangle, or side DE. So if I could get AB congruent to DE. Now, let me pick another pair of sides. Let me pick, say, BC. If I can prove that BC is congruent to what side in the other triangle, I'm all set. Well, BC would have to be congruent to EF. So BC would be congruent to EF. Now, if I want to use side, angle, side, the angle has to be between the two sides. What two angles would have to be congruent? Well, what angle is between those two sides? It would have to be angle B here would have to be congruent to angle E there. So angle B, that's an angle symbol, sorry about that, would have to be congruent to angle E. So if we can prove side, angle, side, then we can say that triangle ABC is congruent to triangle DEF. So we have proved that by side, angle, side. What we're going to do in proofs is figuring out how to get them to work on side, angle, side. Now, in class tomorrow, we are going to be looking at applying side, angle, side to a proof. So you have to know two sides and a pair of included angle is congruent to prove side, angle, side.